Welcome to Infinite Synthetica. In this series, we will learn how to build the ultimate spacecraft, at least within the theoretically possible. We will go from a simple design and progressively develop it into achieving the ultimate spacecraft. A spacecraft that will enable us to travel the cosmos. But first, let's get into space, specifically low Earth orbit, abbreviated LEO. Before discussing the structure of the spacecraft, let's answer the following question. How much energy we need to get into the low Earth orbit? We need energy for three main purposes: for overcoming gravitational pull, overcoming atmospheric drag, and to stay in orbit. But why we need energy to stay in orbit? Imagine if we launch a rocket vertically in such a way to arrive at LEO with zero velocity. The rocket will be pulled back to Earth. We actually need to have enough tangential velocity to stay in orbit. The energy needed to overcome the gravity of the Earth is exactly the definition of the potential energy. After integration, we divide by m to get energy per kilogram. That's more helpful given that the mass of our spacecraft could change. At the end, we found out that for every kilogram, we need 1.87 megajoule to get to LEO. Let's calculate how much energy is needed to stay in LEO. Assume our chip will have a circular orbit. To do that, we need to calculate the tangential velocity of our chip. We can do that by using the centripetal acceleration, universal law of gravitation, and the second law of Newton. We get the formula of the velocity, plugging it into the kinetic energy formula, and we get that we need 30.4 megajoule per kilogram to stay in orbit. Let's calculate how much energy we need to overcome the atmospheric drag. Let's call it aerodynamic energy, which we will define as the amount of work needed to overcome the drag force from the surface of the Earth to LEO, which is approximately 200 kilometers. So the aerodynamic energy equals the integral from 0 to h max of the drag force. We will assume that the air density will drop exponentially going upward. Thus, rho at the altitude h equals rho 0 times the exponential of minus h over the constant big H. Also, we assume that the velocity of our spacecraft is changing linearly, 0 at the surface of the Earth and Vmax at LEO. Thus, V of h equals V0 times h over hmax. After substitution and factoring the constant, get the following equation. Fortunately, this integral has an analytical solution, which we will cover later on. After calculations, we get that the aerodynamic energy equals 6.74 gigajoule. To be consistent with our previous calculations, let's divide by mass and let's assume that our spacecraft weighs 1000 kilograms. Finally, we get that we need 6.74 megajoule per kilogram to overcome atmospheric drag. In the following section, we will cover the steps to solve the integral of x squared times the exponential of minus kx. The trick is easy. We need to get rid of the x squared, and we achieve that by applying the integration by parts twice. After simplifications, we get the solution of the integral equals minus the exponential of minus kx factor of x squared over k plus 2x over k squared plus 2 over k cubed plus c, of course. So we get that we need approximately 40 megajoule per kilogram to get into LEO. But how we can generate this much energy? One simple answer: rockets. So let's explore how they work. Rockets are based on a couple of simple physical principles. Imagine you are in space, farther from Earth, and you throw a ball. By Newton's third law, there is an opposite force applied on you from the ball. And given that you and the ball have different masses, conservation of momentum implies that you and the ball get different velocities. So you can control how much you get pushed by pushing the ball faster or by pushing a heavier ball. Rockets works
exactly the same way. Instead of a ball, we use gas. We push enough gas mass with enough velocity to generate thrust. We use the combustion of a fuel and an oxidizer to do just that. With the help of the throat and the nozzle, we change low velocity gas into high velocity gas. Notice that this structure is more complicated than our analogy because our mass is not constant. We are losing mass through time, which can be defined mathematically by the derivative of the mass with respect to time, which, in addition to the exhaust velocity, directly affect the thrust. Tsiolkovsky's equation helps us simplify the complexities of rocket engines. It links the initial mass, the spacecraft, plus the fuel and the oxidizer, the final mass, the spacecraft, the exhaust velocity, and the change in velocity of our spacecraft. Tsiolkovsky's equation is so useful that we can use it to estimate that we need 25 times fuel mass than the spacecraft. Not practical. That's why second or third stage launching is usually used. We used Tsiolkovsky's equation to drop the mass ratio of our spacecraft from 25 to just 5 by using two-stage launch. Based on the assumption that our spacecraft weighs 1000 kilograms, we can compute how much velocity we need to overcome gravity, atmospheric drag, orbit in theory, which is approximately between 9.4 and 10.3 kilometers per second.
There is three types of rocket engines: open cycle, closed cycle, and full flow stage combustion, and we will discuss the pros and the cons of each one of them. Generally, we need fuel and oxidizer to be pushed with high pressure to the combustion chamber, so we need a mechanism to turn the turbines. The answer of the open cycle rocket engine to this problem is surprisingly a small rocket engine, which we will call pre-burner. We use small amounts of fuel and oxidizer to run the pre-burner, which in turn runs the turbines, which enable us to maintain the main combustion. One of the downsides of open cycle rocket engines is the waste of a portion of fuel and oxidizer just to run the turbines. Closed cycle rocket engines solve this problem by using different amounts of fuel and oxidizer to run the pre-burner, which results gas-rich with fuel or oxidizer, which gets redirected to the combustion chamber. Then, the main combustion is completed. Note that there is two types of closed cycle: fuel-rich and oxidizer-rich. Full flow stage combustion cycle is the combination of oxidizer-rich closed cycle and fuel-rich closed cycle, such that we have two pre-burners, fuel-rich and oxidizer-rich. Each runs its own turbine. In the end, fuel-rich and oxidizer-rich exhaust gases are directed to the combustion chamber. After analyzing three main types of rocket engines, all of them perform the task of elevating our spacecraft to LEO. But what are those substances that, when mixed, will generate this enormous thrust? Surely they are dangerous and rare. That was my thought, and I couldn't be more wrong. Liquid hydrogen and liquid oxygen were used in the Space Shuttle main engine. Kerosene and liquid oxygen were used in Falcon 9 Merlin. Methane and liquid oxygen were used in modern SpaceX Raptor. In our journey to create the ultimate spacecraft, we calculated the total energy needed to achieve LEO. We covered the physical principles behind the workings of rocket engines, their architecture types, and substances that are used to power them. Also, we used Tsiolkovsky's equation to drop the mass ratio of our spacecraft from 25 to just 5 by using two-stage launch. In the end, if you liked the video, like, share, and leave your thoughts and opinions in the comments. And see you in the next video.